All right, welcome to this morning's session. It's my great pleasure to introduce Professor YoungJu Choie from POSTECH in South Korea, who will speak about Schubert Eisenstein series and Poisson summation for Schubert varieties.
Thank you very much, sir. I'd like to thank to organizers for kind invitation. It's great to be here, and I feel very much honored to be part of this wonderful workshop and wonderful to speak for you. So I'd like to talk about the Schubert Eisenstein series and the Poisson summation formula. So if it works.
Click on the window. You click on the window and see if that works.
So Schubert Eisenstein series are defined by restricting the summation, degenerate Eisenstein series to a particular Schubert variety. It occurred in the work of Eisenstein series, Kronecker limit formula, and the connection among Eisenstein series, multiple Dirichlet series, and Kazhdan crystals, etc., in disguised form. So work, for example, by Bump Goldfield, Brubaker, Bump, and Freiberg, so on. Oops. So in the case of GL2, this is known case. You will see it's only two cases. No? In the case of GL3 over Q, it's known that this Schubert Eisenstein series have meromorphic continuation in all parameters, and it's been conjectured that the same holds for in general case. So we revisit this problem. It turns out that one can relate this conjecture to the program of Braverman Kazhdan aimed at establishing generalization of Poisson summation formula. We proved the Poisson summation formula for certain schemes closely related to the Schubert variety and use it to refine and establish the conjecture in many cases. So this is joint work with Jayce Getz in Duke. So let me set up some notation. So G will be a split reductive group over global field. So you may think G as a GLN, F as a Q, B is a Borel subgroup of G, so that it's a triangular matrix. T is a maximal torus of G, and we have a W as a file group. So you imagine as a permutations. Then T hat is a maximal torus of dual group. Here has an opposite root data, and we have a chi mu, a character on the torus, parameterized by this Langdon's parameter mu. Over, we are going to use AF as an other ring of others of F. And the F mu is an element of the corresponding induced representation, so that F mu BG is delta to the half chi mu of evaluate B. B is the element in Borel, and the F mu of G. So that's the setup. So G has a Brouwer decomposition, which is a union of BWB, where W runs over the all vital element. No? So X, which is a flat variety, G modulo B, is a union of namely Schubert cell YW YW is image of PWB in flat variety. And the Schubert's variety is nothing but the characteristic closure of Schubert's cell, which can be written in terms of union of YU, where U is smaller than W in terms of order. So Schubert's Eisenstein series for each W in pi group, EW is just sum of F mu gamma G evaluated at all point gamma over the Schubert's variety of the rational point of Schubert's variety. So this is the Schubert's Eisenstein series. So we are interested in. So if W is the long while group element, say W0, then this Schubert's Eisenstein series is the usual Eisenstein series. So it's automorphic in G. So it's fully automorphic. In general, as you see, this Schubert's Eisenstein series is no longer automorphic in G. So question is, what is this? How to compute this? What is it good for? We like to answer it. We don't know, but okay, so how do we understand this? First of all, we will use a relationship among Bose-Samuelson variety, Schubert's varieties, and Bose-Samuelson factorization. So alpha I, take alpha I as a simple root, then sigma I will be the corresponding simple reflections. So omega, sigma iota 1 up to sigma iota k is a reduced decomposition of W, which is a product of simple reflections. So W is sigma iota 1 up to sigma iota k. Then PJ denote the minimal parabolic subgroup generated by Borel and one-dimensional unipotent subgroup tangent to minus alpha J. Then one can define the action, left action of K copies of Borel on Cartesian product of P iota 1 to P iota k by left multiplication, conjugation, so B1 up to Bk times P iota 1 up to P iota k is defined as a conjugation, but a little bit twisted. So B1, P iota 1, B2 inverse, B2, iota 2, P2 inverse, so on, but last one is just Pk, P iota k. Then quotient P iota 1 product of P iota k modulo, or this k copies of Borel is called Bose-Samuelson variety and denoted as a ZW. Then it's known that there is a morphism between Bose-Samuelson varieties and the Schubert's variety, which I will denote as a PSW induced by multiplication map that sends P iota 1 up to P iota k to product P iota 1 to P iota k. This map is a surjective birational morphism. But on the other hand, the Bose-Samuelson variety are always non-singular, while the Schubert's variety is not. So this map gives a resolution of singularities of Schubert's variety. So I like to explain Bas-Samuelson factorization. So if in the case this Bas-Samuelson map is an isomorphism, every element in Schubert's variety can be written uniquely. Gamma is iota alpha 1, gamma 1, up to iota alpha k, gamma k, where iota alpha I is an embedding of SL2 to G corresponding to a simple root alpha I, so that the image of iota alpha I lies in the Levi subgroup of Pi. This is called Chevalier embedding. Using this factorization, Schubert Eisenstein series can be written as building up the Schubert Eisenstein series by repeating SL2 summation. So when W is a sigma 1 to sigma k, so EW is sigma 1 to sigma k, is Schubert Eisenstein series is summing over SL2 of Schubert Eisenstein series whose length, the length is one smaller than W, which is E sigma 1 up to sigma k minus 1 evaluated at this embedding iota alpha k or gamma k G. Even if this map, Bas-Samuelson map, is not isomorphism, some modification of this method should work. So let me give you an explicit example. So I take G as a GL3. So then K is a O3 is a maximal compact, and the G as a center. Then every element in G can have a Iwasawa decomposition, which I write Y naught times on diagonal Y1, Y2, Y2, and 1. With the Lagrange parameter mu, mu1, mu2, we take this character, delta F here is a modular character times chi of mu, evaluate in this Borel Y1, Y2, Y21 as an absolute value Y1 to the 2 mu1 plus mu2, Y2 to the mu1 plus 2 mu2. So here, I mean, formally absolute value is adelic 1. So F mu of the induced one, the element F mu of G can be written as Y1. This G is from Iwasawa decomposition, or 2 to the Y1 to the 2 mu1 plus mu2, Y2 to the mu1 plus 2 mu2, F of K0, then we take, let's say, the unamplified vector, so that you may assume F mu of K not as a 0. Then here W is generated by two elements, let's say sigma 1 and sigma 2, two permutations. Then G has a Brouwer decomposition, which is a union of PWB. W varies all the elements in the Y group. Then we have Fred variety, which is a union of Schubert's cell. Schubert's cell is in the image of Fred variety of BWB. So then take an algebraic closure, not the Jayce closure of Schubert's cell will give you Schubert's variety. So we are interested in studying this Eisenstein series EW here, F mu of gamma G, where W varies. This element W can be identity sigma 1, sigma 2, sigma 1, sigma 2, sigma 2, sigma 1, sigma 1, sigma 2, sigma 1. They are same sigma 2, sigma 1, sigma 2, which is the longest elements in this case. So when using this Poisson factorization, when W is sigma 1, the Schubert's Eisenstein series E sigma 1 is nothing but GL2 Eisenstein series. So GL2 non-holomorphic Eisenstein series E S tau 1 is a summation of y1 to the s over c tau 1 plus d to the s. So it's a GL2 automorphic form. Similarly, when W equals sigma 2, it's also GL2 object. So interesting case is when W equals sigma 1, sigma 2, this factorization algorithm tells us that E sub sigma 1, sigma 2 can be written in terms of E sub sigma 1 evaluated at 1, gamma 2, this embedding G, where gamma 2 varies all the element in SA to G modulo Borel. So one can compute also similarly. So this is not automorphic either in GL2 or GL3. So these are the cases when the Poisson variety, the map is isomorphism. But note that to reduce the word W, sigma 1, sigma 2, sigma 1, or W is sigma 2, sigma 1, sigma 2, representing wrong element W0. So sigma 1, sigma 2, sigma 1, which is the same as sigma 2, sigma 1, sigma 2. If W is either of these, Poisson map is not isomorphism anymore. But since it is birational, it is a local isomorphism on the complement of some closed variety. Therefore, one can still have a map, a Samuelson map, which consists of discarding the auxiliary piece of data, which is a subvariety of full Schubert's variety, where a Samuelson map has a fiber that consists of more than one point. So by explicitly computing this subvariety, still it's possible to write full Eisenstein series as a sum of Schubert's Eisenstein series, which has a smaller length, namely E sigma 1, E sigma 2 minus E sigma. We have a correction summing over all SL2G element plus GL2 Eisenstein series. So it seems always possible to write every Eisenstein series in terms of smaller one. We have another application. So it's connected with number theory. So connection with the chronicle linked formula for totally cubic field. So expansion, let's consider expansion of Eisenstein series has a pole at mu1, mu2 equals 0. So we look at the, let's say, mu equals 0 expansion. It has a residue. We write residue as a kappa G. Then kappa G appear in the first chronicle linked formula of totally real cubic field over Q. This was done by Bump and Goldfield a long time ago. So connection is as follows. you take an ideal class of K, then one can associate this ideal class to a compact torus of GL3. Then integrate the period of kappa G over this torus will give you LA. Then you look at the partial zeta function associated to this ideal class. Then the canonical limit formula, first limit formula will give you LA. What's the LA? On the other hand, we realize that this kappa G can be expressed in terms of Schubert Eisenstein series at the values integer 4. So in terms of E sigma 2, sigma 1, and E sigma 2, or E sigma 1, E sigma 2, and phi is some Riemann zeta function, plus some constant. This is a very explicit constant which we can write down in terms of special values of Riemann zeta function. So as a result, at the point where the residue is taken, the Schubert Eisenstein series can be promoted to the full GL3 automorphic form in the sense of the following. So for example, you can write down Schubert Eisenstein series, which has a pole at mu equals 0. So you have an expansion in mu. Then constant term here, phi sigma 1g mu 2 can be essentially regarded as a GL2 automorphic form as an analog of log eta function. So if we apply this process to the full Eisenstein series, you can express constant term as a linear combinations of Schubert Eisenstein series, which is so therefore that's going to be a full automorphic in GL3. So linear, even though single one is nothing to do with the automorphic form, but the linear combination can be. So the result with the bump contains the Schubert Eisenstein series, at least for GL3, have a meromorphic continuation to all values of parameters. And this for each W, Schubert Eisenstein series have some functional equation. Furthermore, the Whittaker coefficient of E sigma 1, sigma 2, whose P part is related to the Dimaza character. So this is a generalization of Kessel-Mann-Schleicher formula that express the Whittaker coefficient of Eisenstein series in terms of characters of irreducible representations of L group. And we have a more interesting computation, which. So then, based on this computation, we made a conjecture. We made a long list of conjecture, but let's look at this one. The Schubert Eisenstein series always have, for general G is a reductive group, always have analytic continuation to all variable parameters. Secondly, although they will not have the full group functional equation that Eisenstein series has, they should have some functional equations. And the linear combinations of Schubert Eisenstein series can be entire also, that is, have no poles in any parameters. And it may be possible, based on our computation, to associate a Whittaker function with the Schubert Eisenstein series. We need some average process to get Whittaker expansion. This would be the Euler product whose p part may be expressed in terms of Dimaza characters, so on. So instead of using, I want to see how much time I spent.
35 minutes left.
Okay. So instead of using Bar-Samuelson factorization, it turns out that one can relate this conjecture to the program of Braverman, Kazhdan, aimed at establishing generalization of Poisson summation formula, as I mentioned. So from now on, this is joint work with Jayce. So Braverman, Kazhdan introduced conjecture. Yesterday you saw it, at least. Now called Poisson summation conjecture, generalizing the Fourier transform and the Poisson summation formula. Their conjecture may imply that quite general Lagrange L function have meromorphic continuation and functional application. So it's about functoriality by inverse theorem. Roughly, it is about the existence of a nice short space over spherical variety. A spherical variety for reductive group is a G variety with an open dense B orbit, oral orbit in X, that's the definition. Maybe with some extra, add some normality. So for example, Frank varieties, symmetric spaces are spherical. It seems it's geometry to check whether it's spherical or not.
You know, there is a generalization to have a spherical.
Yeah.
You know, there is generalization statement to have a spherical.
Generalization to what?
Like a spherical.
No, I don't know. Do you know? Yes. Yeah. I don't know. Okay. So at least if it's spherical, there is a theory. I will tell you. Okay. So it was initiated by Braverman, Kazhdan, and defined by NgÄo and Lafforgue and Sakellaridis. I think they defined this Poisson summation conjecture. So conjecture is roughly as follows. The G is a reductive group. X is a G spherical variety with a smooth locus, X smooth. Then there should be a short space called S of X, which belong to smooth function on smooth locus of X. And the map, which is called Fourier transform, f of X, which preserve this short space, satisfying a certain twisted equivariant property under the action of G, which I'm not going to state. It's left and right invariant property, such that for any element in the short space satisfying certain local conditions should have this property. The summation of f of X is the same as the summation of Fourier transform of X evaluated at this smooth locus. That's the conjecture. This is very rough version. This is referred as a Poisson summation conjecture. So known cases, The only case that is completely understood is that of vector space. We know Poisson summation formula on vector space. Then Braverman Kazhdan space. Then triples of quadratic space. Recently work done by Getz and Lu, Getz and Su, and the generalized Schubert variety, which I'm going to talk about, and maybe more. Note that the above case is not necessarily spherical. So we can still have this Poisson summation formula, not only spherical, but also more general. Doesn't have to be. So let me explain Braverman Kazhdan space roughly. So we take a parabolic subgroup of G, which has a Levy decomposition. So P can be written as a Mn. We denote P derived as a P derived group, and NAB as a abelianization of Levy, which is M modulo M derived. Then G modulo P derived, which I denote as XP to the naught, is called Braverman Kazhdan space. So there is a left and right action of MAB cross G on this Braverman Kazhdan space. Action goes as X and G. So M acts on the left, G acts on the right as an inverse. Then I denote XP as a affine closure of Braverman Kazhdan space. That's the notation. So how do we study this space? We use at this time Fluke embedding, which is a map from XP, the closure of Braverman Kazhdan space, to vector space I called VP, which consists of V beta, where V beta is an irreducible representation of the group with highest weight dual to coroots beta. This embedding is a closed immersion, which means it's a morphism, and the image is closed. For example, G is SL to G, SL3. Let's take P equal B. Then you can take a suitable ordering simple root, let's say beta 1, beta 2. Then this representation associated to beta 1, beta 2 are nothing but we can take a standard representation, GA3, and wedge GA3. Then we may choose 0, 0, 1 and 0, 1, 0, wedge 0, 0, 1 as the highest weight vectors. Then as a row, as a matrix row expression, the image of ABC under this Flickr embedding can be written as C, D wedge C. Then you can see the image of this close of Braverman Kazhdan space is nothing but the cone. The points in F algebra R can be written explicitly like CR is a V1, V2, where V1 wedge V2 is 0. So it's a cone. Image is a cone. You can identify. Then this Flickr embedding is also MAB equivariant, meaning that when you take an action, so M inverse of G, then take an image of PL, P is same as PL, PG, twist by omega PM, where omega P is an isomorphism from this multiplicative group B abelianized MAB to some multiplicative law. Another recipe is pairing between two Braverman Kazhdan space. So it goes like this. You take an opposite parabolic, we say P star of P. So you may, if you take P was a Borel, opposite is a low triangular, for example. Then VP check is a representation of G dual to VP. One can see there is an embedding, Foucault embedding again from XP opposite to dual of VP. Since we have two vector space VP and its dual, so there is a pairing VP cross VP head check. It induces a pairing from XP cross XP opposite of XP to GA, which we denote pairing P modulo P opposite. There is another recipe, it's called intertwining operator. So I write a script RP/P star is a map from smooth function over XP to continuous function over the opposite Braverman Kazhdan space, explicitly given by integral. Is defined as f over ny over unipotent element over n opposite unipotent. Then Schwartz space of XP is defined with the condition that Belen transform of F and this intertwining operator, the image of this intertwining operator have poles no worse than some product of gamma factors. So roughly, the Schwartz space of XP belong to the some smooth functions of XP. You can think this way. Then original Braverman Kazhdan defined the explicit unitary isomorphism between L2XP to L2XP opposite. So this is a square integrable space commuting with the actions of a group M abelionized times C by renormalizing the intertwining operator to make it unitary. But recent work by Getz and Su and Lassell gave an explicit formula. I found this is amazing. So this Fourier transform is an isomorphism, same setting, real isomorphism from the space of Schwartz space of XP to Schwartz space of opposite XP with formula Fp/P opposite can be written as a mu P augment composite F geometry, where Fp/P opposite geometry looks like really Fourier transform. It's integral over XP naught F of X. Chi is an additive character like exponential. Then you have this pairing y star P/P opposite dy. And this augmented operator is very explicit. So mu p augment is a map sending Schwartz space opposite to the smooth one, C infinity xp star, given as an explicit integral, which involve again the isomorphism from MAB to some field, and the absolute value to the S plus 1 with the modulo character, and f of m to the minus lambda x, where lambda is some integer, s is a complex parameter depending on the dual of Levy and nilpotent. Okay, so I found this is amazing formula. This is a really beautiful formula. Should have very many applications. So now let's go back to our task. So pursuing Schubert's variety and by Summerson resolution to study higher rank analog, we observe the following observation. So when we look at the Schubert's variety XW, which is the closure of BWB, this is often fixed by larger group than B. Namely, if you look at the X sigma 1 sigma 2, by explicit computation, can be realized as a P21 sigma 1 sigma 2 P12, where P is larger than B, it contains P. So it's a parabolic type 1 to 1, and the other one is parabolic type 1 2. So instead of pursuing Schubert's varieties and Summerson resolution to study higher rank analog of left-hand side of above equation, we look at the right side, we generalize and study right side directly. So we like to define generalized Schubert's Eisenstein series. Sorry. So we have a pair of parabolic subgroup, P and P prime in G. Unfortunately, we have to assume that P is maximal. This is important to prove the theorem, maximal in P prime. And Y can be any variety stable under left multiplication by P prime. For example, Y can be Schubert's variety, which is closure of PWB, or Y can be P gamma H. H can be taken any subgroup of G instead of full group. Then Y as usual, the image of Y under this Braverman Kazhdan space. So P Y modulo P drive. Then one can check this Schwartz space X SYP. So Schwartz space of YP belong to space of smooth functions on XP. And one can also check the Schwartz space of YP is preserved on the left action of MAB. So we get the Mellin transform. We need Mellin transform, which give us induced representation. So the which goes as you take F, then F mu Y is defined as an integral over M abelionized. Then you multiply modulo character, and the character chi mu, evaluate this image of isomorphism omega p, then f of m minus 1, m inverse times y. Then from our choice of Schwartz space, this y f mu converges absolutely for real part of mu 0 large when I didn't write down the other parameters were fixed. So mu can be written as mu 0, mu 1 up to mu k. Then here is a result. So we define the following generalized Schubert Eisenstein series. So you take the f from Schwartz space on yp. You get the Mellin transform by previous processing to get f mu. Then you are summing over this f mu, evaluate gamma g when gamma runs all the element yp modulo mab. This is called generalized Schubert Eisenstein series. Then we prove that with the same setting here, mu, as I mentioned, is a parameter mu not to up to mu k. So we fix mu 1 to mu k such that the real part of mu I is sufficiently large. We just fix. Then this generalized Schubert Eisenstein series, we have two types of Schubert Eisenstein series for yp and yp opposite with different f mu are meromorphic in one parameter mu naught. Moreover, we have such identity. Schubert Eisenstein series on yp G f mu is the same as Schubert Eisenstein series on yp opposite G, then Fourier, you take a Fourier transform of f. That's the usual relation for the Eisenstein series. So to answer the question we raised with bump, our setup is take W as any element even in G, not necessarily the element in W. Then P prime is a stabilizer of closure of PWB on the left action of G. Then we may consider family of generalized Schubert Eisenstein series, so which we denote as we look at the image PWP in Braverman Kazhdan space. Then theorem provides us that when P is contained in P prime as a maximal parabolic, we can have one functional equation of this family of Schubert Eisenstein series with respect to mu naught. And we have meromorphic continuations with respect to mu naught. And if you look at closely the proof of the theorem, or linear combinations of this generalized Schubert Eisenstein series can be entire in mu naught, therefore, for everything, because we fix the other parameter to make it large enough. So to prove theorem, we prove Poisson summation conjecture for yp. And the second thing is we do not know whether this yp, our setup, yp is nothing but the scheme which is left fixed on the P prime, some parabolic elements, you know. Yeah, and YP is image on the image of Y into this Braverman Kazhdan space. Whether this is spherical or not, but many cases seems spherical according to our reference. There is a reference listed. And another, although we worked hard, we proved the meromorphic continuation for one parameter, mu naught, although conjecture, according to conjecture, you should hovers for every mu. So now we are thinking of some kind of induction process to make everything work. So I think this is it. I finished.